All right, physicists, welcome to our January 20th edition of Physics. You should have turned in homework 1 by now. Homework 2 has been posted since Monday of this week, and if everything goes well, it should be due this coming Monday. So today we have quite a bit to cover. We're going to talk about the distance between position and displacement. We're going to talk about average speed and average velocity. We're going to talk about acceleration, and we're going to talk about the relationship between accelerations and velocities. All right, so this is quite a bit, but don't freak out because we have a lot of reinforcement built into the semester. So it's kind of a lot, and then you do the same thing over and over and over. And so hopefully it's kind of like doing reps. You'll be strong by the end of the semester. So just to comment on our force concept inventory that we all took last Friday, the average score for this was 9.75 out of 29. So that's about 33 or 34%. The high score was 19, the low score was 5, and that's out of 29 questions. And I don't think that's too unusual. I do think it shows that we have some work to do, though, because these are very common physics questions that any physics professor would probably get right, but they're also questions that any person who hasn't taken physics might have some trouble with. So the goal is by the end of the semester you're going to knock those out of the park and feel good about them. Now, today we're just going to be talking about one-dimensional motion. Okay? By one-dimensional, I mean just walking back and forth in a line. So if you imagine, basically the stories that we're going to be constrained to tell are going to be, the idea is you would have like a line on the carpet. You have markers that are marked in with masking tape or something like that, where it says 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so that's our story here. And what a graph like this tells you depends on how good you are at reading these graphs. Now, I make a point of this because I guess I feel that your natural human inclination is to look at this graph rather realistically. You say, oh, you're going up a hill, then you go farther up a hill, then you wait on top of the hill, and then you slide down it. Now that's not so wrong, but in fact what it's talking about is going forward and backward in position. So for instance, what's happening in this graph is that in the first 4 seconds, you're only going 2 forward. And then in the next, from 4 to about 6 seconds, in 2 seconds, you're going to go from 4 to 6, you're going to go from 2 to 10. So you're making going much more quickly. And then from 6 to about 8.5, I guess, you're going to be just hanging out, not moving at 10. And then you start moving backwards. So essentially it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you're going slow, fast, hang out, fast, slow. Now, I only make a point of that because I think in this unit especially, once we start talking about dropping things and that sort of thing, it becomes confusing to realize that you're always just working in one dimension. That could be up and down, it could be back and forth, but we're always just going along essentially a number line. Now, in chapter 2, you can imagine yourself as being this object carrying a watch around with you, always checking the time, always noticing where you are. Now, it doesn't really matter where you put the 0 because we're allowed to go into the -1, -2, -3. 0 just is, you know, it's a choice for convenience. Now, of course, going in the positive direction means the numbers are getting bigger. Going in the negative direction means the numbers are going smaller. So those things make a difference. But we want to be very careful and to make a distinction between displacement, which can be positive or negative, and just distance. So for instance, if I go from -2 to 3, from -2 to 3, that would be a displacement of +5. And the sign would make a lot of difference because it would mean that I was going in the positive direction. On the other hand, if I went from 3 to -2, that would be a displacement of -5 because I was going backwards on the number line. Okay, so just be careful, and we're going to have an analog to this. So we have distance versus displacement, and for motion we're going to have speed versus velocity. So the sign of the displacement tells us about the direction of the motion, and if we care about the direction of the motion, if we want to characterize the type of movement we have, we should probably use velocity instead of just speed. Speed tells us about total distance that we traveled over the total time. Velocity tells us about the displacement over the total time. And notice this is the average velocity. The average velocity only depends on where you ended up and where you started out. And so it's perfectly sensible to talk about a velocity of +3 meters per second. That would mean you're going in the plus direction, or a direction of -3 meters per second. That would be going at the same speed, but backwards. Now, if we're going to retell this story, how would we do it? Well, here you have a positive velocity that's small. Here you have a positive velocity that's bigger. Here you have a velocity that's 0. Here's a velocity that's more negative because you're going backwards and you're going fast, and here's one that's slightly less negative. And the thing I want you to notice about this is that because change in distance or change in displacement over the change in time, this should allow us to make a connection with this type of graph and the velocity. The slope of the position versus time graph gives you the velocity. And if you just took that without the sign, it would give you the speed. Now, as I said a moment ago, the average velocity only depends on the total displacement and the total time. But the slope at each moment is going to give you an instantaneous velocity. So you notice while you're driving, you have one speed, and you're going much more quickly. And then once you start walking, you have a different speed. At each one of these, each one of these regions, the speed that you're going at that time is given by the slope of the position versus time graph at that time. However, if you just want the average velocity over an entire range, you just need the point where you started and the point where you ended, and the line that connects those has some slope, and there it is. It's the average velocity. Now, those of you who have taken calculus know that one of your conditions here is that if this is a differentiable curve, there has to be some position on this curve where the slope is the same as that curve. So anyway, you can look up your fundamental theorem of calculus. All right, so let's look at a problem that just uses this idea. This is one of your homework problems for this coming Monday. It says a car moves uphill at 40 kilometers per hour. and then back downhill at 60 kilometers per hour. What is the average speed for the round trip? Now, the problem with this is that I would like, if I'm going to look for an average speed, I would like to have some sort of final position, initial position, some kind of final time, initial time, but I don't have any times in here. I don't have any positions in here. So it looks like I have a tough time ahead of me. However, let's just realize that it actually doesn't matter. You can choose any length you want. So when I do the problem, I would choose a length of delta x. Maybe it'll be easier, though, to see how this works if I use 40 kilometers. All right, so you're going 40 kilometers up the hill and 40 kilometers back down. So uphill, for instance, my delta x would be 40 kilometers, right? If I'm going to then look at my speed, my v in that region is going to be 40 kilometers per hour. V for that part of the trip is going to be delta x over delta t. And if I want to find my delta t, it's going to be delta x over v, which in this case, 40 kilometers divided by 40 kilometers per hour is just going to be 1 hour. On the other hand, when I go downhill, my delta x again will be 40 kilometers. My speed in this case is going to be 60 kilometers per hour. And my delta t then would be delta x over v. In this case, it's going to be 40 kilometers over 60 kilometers per hour. 40 divided by 60, that's going to be 2/3 hours. So if you wanted to find your total speed, it would be the total distance you traveled. So that would be 40 kilometers plus 40 kilometers, all divided by the total time. That'd be 1 hour plus 2/3 hours. And I'll let you finish that. However, the average velocity, this isn't what the problem is asking for, but if you're going there and you're coming back again, you're ending up at the same position where you end up. The average velocity, you know, has to be 0. Why? Well, because the velocity there is positive, the velocity back is negative, and so that's how you can end up with an average velocity of 0, even though you did a bunch of traveling. Here's another homework problem, similar idea. It says compute your average velocity in the following two cases. I'm going to work through the first one. You can try the second one. For case A, you walk 73.2 meters at a speed of 1.22 meters per second. So here's your x in meters. Here's your time in seconds. And that 1.22 meters per second, that's the slope that you have. And then run 73.2 meters at a speed of 3.05 meters per second. So my slope is going to be steeper there, but the distance that I cover is again going to be 73.2 meters, or 73.2 plus 73.2, I guess would be 146.4. You can check my math on that. And the slope here is going to be 3.05 meters per second. Then it asks us to compute your average velocity. And we made our graph. How would I find my average velocity if I had all of these points in order? I would take the slope here. The slope of that is V average. All right, but I don't have this time. Let's call that T1. And I don't have that time. And so it's going to be hard for me to go ahead and actually find that, that average velocity. Okay, well, how would I do it? Well, for part 1 of my course, I do know the delta x, which is 73.2 meters. I know the v, which is 1.22 meters per second. And then you can find the delta t. And then for part 2, again, you know the delta x, 73.2 meters. You know the v, which is 3.05 meters. And you get to find the delta t is what? Okay, so just use v is delta x over delta t to solve for delta t. And then once you want your v average, it's going to be your total distance over your total time. So that's going to be, in terms of this, it's going to be 146.4 meters over t2, which is going to be this delta t plus that delta t. Okay, so this plus this is going to be the time that you use. All right, so a couple steps thinking about it, but once you have all the steps together, it should be sort of straightforward. Now, since you've taken calculus, you've thought some about rates already, and you can probably guess what I'm going to do next. Instead of just looking at those averages, we're going to start squeezing down the amount of time that we're looking at. And we're going to look at shorter and shorter time spans. And as we do that, we can imagine a limit as the time span that we looked at goes to time equals 0. And at that point, you would think about your instantaneous velocity. Now, your instantaneous velocity is this, you have some experience with this. Imagine the number that you read off of your speedometer as you zip around Shreveport. That is effectively your instantaneous speed. Instantaneous velocity has a direction component as well, but the idea is there. Now, so here's our position versus time graph. As we said, the slope at any given point tells me how what my velocity is. So if I want to find my velocity, I just take the slope, which is the derivative. Okay, derivatives are slopes. Integrals are areas, but we'll probably get to that next time. Now, in this particular case, you see the velocity versus time. So this is a case where our particle is getting faster. It goes at a steady rate for a while, and then it gets slower and stops. Now, if you're looking at the velocity versus time graph, it can be a little confusing because this makes the fact that a flat graph in position means you're not moving. When we have a flat graph in velocity, it doesn't mean we're not moving. It just means that our speed and our velocity is staying the same. So here we have our velocity is changing. We're getting faster. Our velocity is staying the same. You can see that as a steady rate of moving forward, and here our velocity is slowing down, but I'm still going forward because it's still a positive number. However, the fact that we can look at slopes on our velocity graph gives us an idea. And that idea is that maybe we could also look at how the velocity is changing. Okay? And so you can think about this number is called the acceleration, and it is the velocity. If you want to find an average acceleration, you would take, for instance, the average acceleration here. You would take the speed at the end minus the speed at the beginning, divided by the time at the end minus the time at the beginning. Okay, that's exactly like before. We're just finding rates. And again, the same sort of idea. If we wanted to find the instantaneous acceleration, we would take a derivative. So the derivative is the slope, so it's the slope of the velocity graph. Two things to notice. Of course, A is dv dt, but this is d dt of our v, which we said was dx dt. So our acceleration can also be thought of as the second derivative, d squared x of dt squared, the second derivative of the position. So that's one thing to think about. The other thing to think about are, what are the units on this? Well, acceleration is change in velocity over change in time. So velocity has units of meters per second in our most friendly SI case, and time has units of seconds. So this acceleration has units of meters over seconds squared. So that's meters per second per second. So how is your speed, how is your velocity changing per unit time? Now, in my last, we were trying to draw a picture of position versus time and interpret that. We can also draw pictures and interpret them for velocity versus time. So, here, let me make sure that's a V. What does a velocity versus time graph mean? Here's probably the simplest one. Our velocity starts at 0 and it gets more and more positive. So this is just go forward and getting faster. Okay, so that's the simplest one of that. The sort of equivalent one going backwards and get faster. Okay, so those are pretty easy to interpret. But some of these you have to look at a little bit. Okay, so for instance, what does this one mean? Now, if I'm looking at the slope on this thing, it's positive, so the acceleration must be positive, but what's going on? Well, at the beginning, here's my 0 velocity. So at that point in time, it must be not moving. V is 0. What is V happening in here? Well, I'm going backwards. How do I know? V is negative. Negative velocity means you're going backwards. So you're going backwards fast, you're slowing down, slowing down, slowing down. Stop. Start going forward. Go forward faster and faster and faster. All right? And then here is the opposite of that. You start out going forward fast, you slow down, slow down, slow down. Stop. Start going backwards, get faster and faster and faster and faster, going backwards. So in these ones, you're going to be changing direction. Okay, so you're going from backwards to forwards, and you're going from forwards to backwards. Now, I gave you a couple of homework problems with this instantaneous velocity. I think it's pretty easy, except for maybe you have to, dust off your bookshelf with the calculus book on it. So let's look at this one. It says an electron moving along the x-axis has a position given by x equals 16 t e to the minus t meters, where t is in seconds. How far is the electron from the origin when it momentarily stops? Now you might look at that and say, I don't know what the heck that means, or what it looks like. But you can always plug it into your graphing calculator, or I went to desmos.com and typed this in and had it in a couple seconds. So it says, how far is the electron from the origin when it momentarily stops? Well, this graph says to me that you're going forward, 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 stops, turn around, come back, 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 back. And you get almost back to where you started at time equals infinity. So they're asking us, how far from the origin is that? Well, here's how I would do it. I would go x equals 16t e to the minus t in meters. And then my v is going to be my dx dt. Now this is where you might have to dust off your calculus book. You have to remember your chain rule. So you take the derivative of this times that, plus the derivative of that times this. So derivative of 16t is just 16 e to the minus t, plus, and then we're going to have just 16t, and the derivative of e to the minus t is minus e to the minus t. Okay. Now, when does it momentarily stop? Well, when it's stopped, our velocity will be 0. So 0 equals 16 e to the minus t, plus, let's factor out that minus 16 t e to the minus t. Okay, well, I think that you can see what happens here. Multiply the whole thing by e to the plus t, and this would be just 16 minus 16t. You get t equals 1. Stick that in there and find yourself a solution. Okay, so this one I think is not too bad. I think the other one I gave you with instantaneous velocity is also not too bad, because I give you the particle's position, 4 minus 12t plus 3t squared. Okay, taking the derivative, this one will go away. This will just be minus 12. This one will be 6t, and then that'll give you your v, where your velocity is positive. That means the particle is going forward. Where it's negative, that means your particle is going back. So I'm not going to work through this one with you. I would like you to try it. If you have questions about it, shoot me an email and we can try it on Friday. Now, throughout most of the first unit, we're really going to just be playing with a single model. And this is the model for constant acceleration. Now, constant acceleration is where the a is the same as the a average because it's not changing, and it's just v minus whatever speed you started out with divided by t. So the acceleration in this case is just flat. It could be 0. In that case, this term and this term will fall out, but we'll be okay. So what is this model saying? It's saying we have a constant acceleration. That means we're going to have a speed, a velocity here that depends only on the initial velocity, that's whatever velocity we start out with, and the acceleration. So the acceleration is fixing all of our behavior in time. And then our position in space is going to depend on where we start out in space, our initial position, and it'll depend on our initial velocity, and it'll depend on that acceleration. So just to spell this out more clearly, we have x is our position at time t. X naught is our position at time t equals 0. V is our velocity at time t. V naught is our velocity at time equals 0. And then our acceleration is constant in time. Okay, so it's not changing. Now, I'm not going to push us all the way through this model today because working out all of the intricacies of this takes a little work. What I want to stress, though, is that this model actually covers quite a few situations. So for instance, each one of these situations that we discussed earlier is in fact a constant acceleration problem. How do I know it's constant acceleration? Because the velocity graph has a constant slope. So it's just a flat, it's not a curve, it's just a line. And I ask the question here, which graphs have a positive acceleration? Well, positive acceleration means positive slope, so that would be these two graphs. But I just want to bring to your attention that positive acceleration can mean different things in different circumstances. So for instance, positive acceleration in this case means exactly what you think it means. It means that our speed is getting faster. We're going forward, we're getting faster. On the other hand, if you look at this one, positive acceleration the whole time, it's just the slope of the velocity versus time graph. However, here you're going backwards but getting slower. So going backwards getting slower also has a positive acceleration. The way that your velocity is changing, it's getting more positive. But that can mean different things depending on the situation. So these are positive acceleration. These graphs have negative acceleration. How do I know? Because acceleration is dv dt. It's the change in velocity over the change in time. So if that is, if velocity is becoming more negative, my acceleration is going to be negative. This is a negative slope. Okay, so I gave you a homework problem with this. It says at a certain time, a particle had a speed of 18 meters per second in the positive x direction, and 2.4 seconds later, it was 30 meters per second in the opposite direction. Okay, so you're starting going one way, you're ending up going the other way. What is the average acceleration of the particle during this 2.4 second interval? Okay, so the average acceleration is going to be the final speed minus average, the initial speed over the final time minus the initial time. Or you could plug it in here where this would be your final time, or final velocity, this would be your initial velocity, this is your acceleration, which you would solve for, and your time. That would be okay too. In this case, however, let's just think about it. At a certain time, a particle had a speed of 18 meters per second. Okay, so that would be 18 meters per second would be your initial velocity. And 2.4 seconds later, its speed was 30 meters per second. What is the average acceleration of the particle during this 2.4 second interval? So then I would put in 2.4 seconds here and 0 seconds there. And I just want to caution you because there's sort of a temptation to just put in 30 minus 18 over 2.4, and then you get some number. It has units of meters per second, so meters per second squared. Everything looks good, but notice 30 meters per second in the opposite direction. So this is a case where velocity matters. Okay, so if this is a different direction, I would have to put a minus 30. So I'm going to have a minus 30 meters per second minus 18 meters per second. That's a positive over 2.4 seconds. And that'll give me the right answer, because I'll have minus this, and we'll get 48 over 2.4 meters per second squared. Okay, so I think that's enough for today. What are our big ideas? Distance and speed don't have signs, plus or minus, while velocity and displacement do. An average velocity is found by dividing the total displacement, not the total distance, the total displacement by the total time. And acceleration tells us how velocity is changing over time. And we're going to use units of meters per second squared for that. And just as a peek towards the future, we can model many different types of motion with our constant acceleration model. Okay, so for Friday, please take a look at the homework. Please try to see where your questions are. You should be able to do most of the first page of the homework just with what we've done here today. So please take a look at it, bring some questions for Friday. Good luck.